All right, so the last piece of our puzzle is actually bringing our Kc and our Kp back together. Remember, Kc is the equilibrium constant for concentrations, while Kp is specifically for the equilibrium constant of pressures. If you measure the pressures of the system versus the concentration of the system, that's going to depend on what you have. If you had aqueous systems, you'd want concentration. If you're working with gas particles, that's when you'd start to kind of interact with the pressure portion. And so there's a way using the ideal gas law that we can start to bring these back together. I'm going to show it here briefly. Don't worry about the derivation piece so much. All you need to know here at the end is kind of this overall arching or this important formula. So for our ideal gas law, we know that PV equals nRT, P being pressure, V being the volume, N the number of moles, R being constant, and T being the temperature in Kelvin. Turns out you can divide over the volume, and you end up with N over V. Well, N over V is the same as molarity. And so you can actually sub in for that N over V portion, molarity. And keep in mind when we say Kp versus Kc, that for like this reaction here, their setups, their powers, their exponents are proportional. They're kind of the same. The two expressions are measuring the same relationships. It's the same products over reactants. It's just whether or not you are working with pressures or concentrations, but all the other numbers, everything else is kind of the same. And so it's just what it is you're actually measuring, atmospheres versus molarity, which means we can actually kind of take all these different pieces, sub them together, and we end up with this really handy kind of conversion formula. That's really what this is. This lets us go from the equilibrium pressure constant, our Kp, back to Kc, or vice versa. A couple of notes here. R is the other universal gas constant. It is the smaller one. It's going to be our 0.0821. There's a bunch of them on your equation sheet. This R is going to be that 0.0821 liters times moles. Yeah, liters times atmospheres, excuse me. Liters times atmospheres over mole Kelvin is the R we're going to want for this one for our gas constant. T is your absolute temperature in Kelvin. N is your number of moles of gas product minus your moles of gas reactant, because that's really what's going to be creating the stark difference in pressure is how many more particles of gas you've got created versus what you started with. But at the end of the day, it all kind of comes back to this formula, Kp equals Kc parentheses RT to the delta N. Now keep in mind how those exponents are going to kind of factor in here. The RT are all being raised to the delta N. The Kc is not. It's going to be important here as we're kind of looking at some examples. Speaking of examples, let's look at a couple examples. So let's say we were given the following information. Chemical engineer injects limestone calcium carbonate into a hot flue gas of a coal burning power plant to form lime CaO, which scrubs the sulfur dioxide and creates acidic gas. So this is actually one of the ways we can kind of control our pollution from some of our larger coal burning plants. Find Kc for the following reaction if CO2 pressure is in atmospheres. So here is our reaction. We're going to need that. We know the Kp and we know the temperature at 1,000 degrees. We want to know then what the Kc would be. All right, well, this is a little bit different. We know that Kp equals our Kc RT raised to the delta N. Real quick, let's find our delta N. Looks like we had one molecule or moles worth of carbon dioxide present on the product side. We don't got any on the reactant side. So our delta N, products minus reactants, would be 1 minus 0. So N is going to equal 1. Oh, that makes the math kind of nice. I dig that. Cool. I'm plugging what I know so I can solve for what's missing. Looks like I know the Kp. Our Kp was 2.1 times 10 to the negative 4th. That's going to equal some Kc we don't know. R is 0.0821 times our temperature, which was 1,000 Kelvin, all raised to the first. So to solve for Kp, I think we're going to have to divide over that right-hand side. Going to be divided by 0.0821 times 1,000, all raised to the first power, which is just that value. When all is said and done, plug that into your calculator. I think you should get 2.6. 2.6 times 10 to the negative 6th for your Kc, if you were to actually measure in concentration as opposed to pressure. Again, we're just kind of looking at how we can start to use what we're given, depending on what substances we are measuring for our equilibrium constant. Cool, one more for you. Up. Yay. Do I want to save changes? No. Cool. Given a Kc of 55.3 at 21 degrees Celsius for the below reaction, what would the Kp be? Cool. Go ahead and pause real quick. Give it a shot. See what you get. Cool. As you go to set this up, don't be mad. Hey, don't be mad. Reminder, Kp equals Kc RT all raised to delta N. If you plug in what you know here, again, don't be mad. We had 55.3, R was 0.0821 times our temperature, which was 21 plus 273, which is 294. All raised to the, we had 2 gas particles on the product side. 2 gas particles on the reactant side. 2 minus 2 is 0. And here is an important fact for us to know. If the number of moles of gas are the same, your Kp will equal your Kc. I'll say it again. If your delta N of moles is 0, your Kp will always equal your Kc. Cool. Armed with this information, you can solve a variety of different problems. Hopefully we're feeling pretty good. We've got some practice to be looking at.